Hello, folks. Let's get on with the AWS Aurora Immersion Day workshop. And this one is this video. This one's going to be about Graviton 2 versus x86 performance. So this lab compares the performance between x86 instance and Graviton 2 based R6G instance class. So this lab contains the following tasks: add a new x86 based R5.large Aurora replica, simulate online transaction processing workload with Sysbench using the Graviton R6G.large instance, promote x86 based R5.large Aurora replica to become the primary, and repeat the simulated OLTP, that is online transaction processing workload using Sysbench using the R5.large primary instance, compare the results, clean up lab resources, right? So I think currently, let's see what kind of instance we have here. This is the R6 large actually, right? So Graviton 2, it's basically R6 large is Graviton 2. So we have R6 dot large only now, right? So you'll notice AWS Graviton. You'll actually see this Graviton, and I think Graviton 2 probably shows up. I don't know. Let's continue with this Graviton 2. Yeah. So I think if you look at which ones are Graviton 2, if you click this, okay, this just goes to the console. Quickly innovate with Graviton fast start. Okay, I think this is probably a okay, get up to 49 for a variety of Graviton fast start. I don't know fast start, what is this increased performance one? RDS, okay. Not sure what's the difference. It's a program, okay, helps you quickly and easily move your workloads to AWS has translated this work for many templates such as workloads. Okay, so looks like it's a program, and anyways, so available as managed sources, EC2 C8 GN instances. Okay, I think in instance types, for example, probably in pricing it might come up, Graviton savings dashboard, sustainability overview, customers, partners, getting started. Okay, so get started for free with P4G, and then what other instance types do we have? Is there R6? No. So let's look at I think let's look at Graviton 2. Let me see if that is there. No. Graviton processor, Graviton 2 based instances. So this is AWS Graviton processors, and it is ARM. Okay, it doesn't say ARM now. What's the difference between Graviton and this? Let me see. It's the same thing. Yeah, it's the same thing. Cool. So R6G. Yep. So you can actually see that R6G are available. So Graviton 2 based EC2 instances are available in additional regions. So Graviton recent is Graviton ready program partners. Okay. So a transition guide, GitHub repository, porting advisor. Okay, cool. So you can actually click these R6 instances, R6G. So these are based on Graviton, I believe. ARM based AWS Graviton 2 processors. Yeah. So it's ARM architecture. So yeah. So now let's look at just a moment. Is this uploading some stuff? Anyways. Now let's look at this, and we'll be looking at x86 based R5 large and comparing it with this. the existing thing, right? So the lab environment that is provisioned for you already has an Aurora MySQL DB cluster with 2 instances, one writer and one reader, running on r6g.large Graviton 2 instance class. Open the thing. If you don't already have it, click the reader button and click actions and click add reader. Okay, so let's go ahead and add reader. So you can't add reader here, but you can click this and add reader here. So add reader. Okay, so type Aurora Lab MySQL x86 node 3 as a DB instance identifier and select db.r5 large x86 instance class. Okay, let's just copy this node 3. Replica source, we'll have to see. Let me put replica instance identifier. Is that replica source is 1 or is it 2? It should be MySQL node 1 parent writer instance. We need the writer only, not the reader instance. So let's just put it as writer instance. I think accordingly things will change, I'm not sure. Anyways, writer instance, and this is there, and include previous generation classes. Nah. R6 large is basically Graviton, so I want db.r5 dot large r5.large. This is what I want. Let me just double check. x86 instance class. So oops, yeah, cool. And memory optimized, burstable. Okay, includes R classes, serverless. Okay, the replica database will be in the same region as the source database. Makes sense. Publicly accessible? No, not publicly accessible. And cool. Set failover priority tier to tier 0 to ensure that this instance is available as a failover target. Leave the rest of the configuration to default. So where is the failover thing? Failover priority tier 0. Awesome. There are tier 15. Failover priority. Okay. Add reader button for okay. Cool. Let's just go ahead and add the reader. So let's just a moment. Yep. So is invalid or does not include the required permissions. Enhanced monitoring. Okay. Just a moment. Writer not to availability zone. Authentication. I don't need IAM. So I'm wondering role ARN value invalid. Okay, that's created. It was a weird error. I'm not sure what that error meant. But okay, so consider creating a blue-green to minimize downtime during upgrades. You may want to consider using Amazon RDS RDS user guide. Aurora this. Let's just copy this up and these up and have it here. Yeah, and here I just get these in. Anyways, and then Aurora user guide and then RDS user guide, Aurora user guide. Okay, this one learn more here, and what is this about? So this one says something about reducing downtime, minimize downtime during upgrades. Provide the staging environment for changes to production databases. Easy path homogeneous data migrations from EC2 database to RDS. So if you are self-hosting, so yeah, with integrated homogeneous data migration powered by DMS, I think data migration system. The Amazon RDS console leverages simple and performant data migration from EC2 database to equivalent RDS database. To get started, select an existing RDS database and choose the migrate data from EC2 database in the Actions menu. Make sure you check the supported engine types and feature limitations. Introducing global database writer endpoint. Each global cluster now has a writer endpoint that you can use to send your application's requests to the writer instance in the primary cluster of your global database. Aurora automatically updates the endpoint upon a cross-region failover or switchover operation, ensuring that requests are routed to the writer instance in the new primary cluster without the need for changes to your application code or configuration. Interesting. That's what we had checked out here. And introducing Aurora IO optimized. It's a new cluster storage configuration that offers predictable pricing for all applications and improved price performance ratio with up to 40% cost savings for IO intensive applications. Okay, cool. Okay, so now I'm gonna close these up and I'll write this down too. Run the track, run the track, run the track, run the track. Okay, that's just a song. Sorry. Okay, so we have added a reader. So this is the thing. This is the cluster, and you can see that there's a reader instance. It's still in creating state. So it's in 2C. Right, so the engine is Aurora MySQL. Cool, so it will take a few minutes to add a new x86 instance to the cluster. In the meantime, follow the next lab. If you have not already opened a terminal window, we have already opened it. So once connected, create this. So let's run this. SQL. So let's look at this one. Probably need this, not proxy, this one. This one is available twice, and so we're just gonna close this, but not my lab. I think this is gonna go to the default one. Let's look at that. Connection info. Does it have anything? No. Show tables. No database selected. So no database is selected. Show databases. Alright. So MySQL is a database we are currently connected to again. So we'll create the database graviton test, right? And then quit. Quit. Or we can even say exit, I think. Yeah. Cool. So now in the base code, I need to run the following command to populate the tables with sample data. It will take approximately 10 minutes to finish populating the data to the tables. Replace cluster endpoint with your cluster endpoint. Okay. Copy this. I think this is sysbench cutting. I think we have this. We have this in sysbench. Okay, wait a moment. Local share sysbench. Okay, so this is probably not present. Yeah, I think this is something that's present only here in this machine. Okay, so first let's put the cluster endpoint here. So bash, and I'm gonna just copy this and put it here, and let's see what this is all about. So we have this sysbench tests and whatnot. I can probably copy recursively this thing. No. recursively copy this into sysbench files, okay, in the local, and let's see if that is there. Sysbench files, yep, awesome. So I can actually copy this and put this down, right? Download, yep. I think this should come up here. Yep. Cool. So with this, I'm just gonna go ahead and run this. It's preparing the sysbench, I think. Okay. So this will take about 10 minutes apparently. So let it run. So it's going to the Graviton test database which we just created. Yeah, we just created it here only. So Graviton test. So now it'll take a few minutes to populate the data. Once it's been successfully populated the data, we can start the load test. Run the following command to start the load test on an x86 instance. Replace cluster with a okay, how do I run it on the x86 instance though? Replace cluster endpoint with the Aurora cluster endpoint. That doesn't make sense. Okay, so we are running it on the Graviton 2, I think. Anyway, so after letting this test run for 5 minutes, observe the CloudWatch metrics instant by clicking on the Aurora Lab MySQL Node 2 or your current writer instance. Next, click on Monitoring tab, review resource utilization metrics like CPU utilization and freeable memory. Next, review database related metrics like select throughput, DML throughput. Oh hey. After reviewing the metrics, select MySQL Node 2 or your current write. Navigate to the database insights from the monitoring drop down. From the database insights dashboard, review the database load and wait events. Okay. Where you can see most of the weight is related to CPU and IO. Next, also review the top SQL. Select database telemetry and select create widget. Individually create separate widgets by selecting the following options under SQL and transactions. InnoDB rows inserted, updated, read, active transactions. Once the sysbench workload completes, you should see results similar to the following database telemetry. This shows the number of rows read, inserted, updated from tables and active transactions. It has increased a lot. Okay. After reviewing the database insights, head back to the VS Code and copy the results of the sysbench SQL statistics from VS Code terminal to Notepad. We'll use it to compare the results at the end of this lab. Okay, so SQL statistics. Cool. Let this run. I think this itself will take some time. We need to run the next thing as this. Okay, let this run. In the meantime, I'll actually go ahead and check out what they say next. Promote x86 based db.rfi.large Aurora replica to primary instance. Okay, now let's fail over to the x86 based db.rfi.large Aurora MySQL instance. Select any instance of the Aurora cluster and then select failover in the actions menu. Okay. So I don't know why this one. Okay. So I don't know why they chose this one. Okay, the writer instance. Okay, but I think you can choose anything. I'm not sure. If you say failover, there's no failover option here. Fail. Nope. What about clicking on this and saying failover? Yeah, but this is a reader instance. That doesn't make sense. Is there a failover option here? Yeah. This is a writer instance. That does make sense. Failover. Interesting. You can choose failover on anything. Huh? I'll probably try that now. I don't know. On the reader instance to see. Confirm the failover action in the next thing. Are you sure you want to failover my... Okay, yeah. This talks about the cluster only this time. Wait for about 30 seconds and refresh your browser window to verify that the Aurora MySQL x86 node 3 instance has become the new writer instance. After you've confirmed that this is your new writer, you're going to simulate the same OLTP workload in an x86 instance. Okay, so great. So it's creating some secondary index and whatnot. It's inserting records, and it's almost going to be done, I think, because it was running for a long time. This is going fast based on after adding indexes, I think, or indices. Yep. So okay, so repeat the simulated thing. This time you'll repeat the same thing, I think. Read write. Okay, I think it's the same thing, right? Yeah, it's the read write run here. The data is the same. Now you'll run it, but now this time it will run on db.r5. So we still have the data already on the database, and there's a replica which will have the replica has already gotten all the data. So now it will also have the data, and when it becomes writer, and it will have the data, and we'll just run it. It will run for 10 minutes. After letting this test run for 5 minutes, observe the CloudWatch metrics by clicking on the Aurora Lab MySQL Node 3 or your writer instance. Click on the monitoring tab, review resource utilization metrics like CPU utilization, freeable memory, this much memory you can free and whatnot. Apparently, we can see all that. Next, review database related metrics like select throughput, DML throughput. Okay, this is going to take some time, so this is way. So basically, look at the metrics. After reviewing the metrics, select the new writer instance. Navigate to database insights and from the monitoring tab in the RDS console. Okay. From the database insights dashboard, review the database load and wait events. We can see most of the rate is related to CPU and IO. Next, also review the top SQL. Okay, so finally select database telemetry, and since we created the widgets in the previous section, you should be seeing separate graphs for InnoDB rows inserted, read, updated, and active transactions. Once the sysbench workload completes, you should see results similar to the following in database telemetry. Okay. After reviewing the database telemetry metrics, head back to the VS Code IDE desktop and copy the results of the sysbench SQL statistics from VS Code IDE terminal to Notepad. We'll use it to compare to the results at the end of this lab. We have run a sample workload in both Graviton 2 and x86 instance classes. In the next section, we'll compare the results. So results from Graviton 2 based things. Queries performed, read, write, transactions is 492. This is 4 million, I think. Yeah, 4.1 million, 1.1 million, and then other is just 590k. Total is 5.9 million. Okay. This one, it's 2.64 million. Man, okay, that's very less. Right is more, is it? No, this is 11 million. Oh wait, no, this is 1.1 million. Right here, oh, it's 750k. That's less. Other 377k. Total 3.7 million. That's less actually. Transaction 314.54. Okay, so that's pretty less basically. So you can actually see that average rows read, not roads, average rows read per second is 140k versus Graviton 2 based thing is average. Let's look at average. How come? I think they're looking at 413 divided by 590. I don't know. No. Average rows read per second. Anyways, inserted. They're looking at these. Average rows inserted per second 340, 500. So there's actually a lot of difference basically. and updated transactions. Interestingly, I'm just wondering where did they find these exact things? They're saying transactions, yes, but where does it say comparing results from SQL statistics from each run? These are the average rows read per second, average rows inserted. So basically, CRUD, create, that is insert, read, update, and then transactions is Sysbench transactions per second is 314, 492, 44%. Cool. So price comparison. So you have taking the above metrics into consideration. Let's examine the cost efficiency of the tested instances for the given sample workload. The cost for x86 is 0.29 and for Graviton is 0.26. So you get, based on the above comparison, is 10% cheaper with 33% more TPS. On the provisioned on-demand instance cost of Aurora MySQL in the US West 2 AWS region, where your results similar to the posted those presented here. Each workload is a little different in using data, and a repeatable methodology is key to evaluating which processor architecture will achieve the best results. For a given workload, as you saw here, choosing the best Aurora MySQL instance type for your workloads can enable meaningful cost savings with increased performance. Cool, so looks like this has run. So I'll just copy this and I'll put it here. Yeah, and then finally I think the previous one was prepared. Now I can just run and then start looking at not here. I can look at how to run this. Yeah, it's basically the same thing, read write. Instead of preparing, this time I'm actually going to run it. It's 306 tables 25 and table size is this MySQL DB is not mentioned. Oh, it's mentioned here. And then time and so it's going to be run. Report intro is this. Let's just run it now. Cool. So now we're going to be actually looking at this. Cut this off. Cool. So I think we have a bash here. Probably don't need it. Get rid of that. Some Amazon, some run suspense thing, I think. Anyways, cool. So now I'm gonna actually go ahead and check out the performance in these clusters. So I can use this also, log insights, database insights and all. Database insights, and there are 3 instances. This is node 2, the writer, I think, and this is the reader 1 and 3. I think the writer is node 2, yep. And summary, high severity, medium severity, DB instance shutdown, this created shutdown. Okay, why did it die? That's weird. So creation, shutdown, restarted, and then creation. Okay, looks like it's mostly good. and then low severity 5, CloudWatch logs, export enabled for this, Aurora, MySQL x86, yeah, of course, and cluster topology is updated, of course. So once insights has been enabled, monitoring interval changed to 60 seconds, I guess, and then finished updating DB parameter group. Okay, cool. Okay, so now I'm just gonna look at this. Just gonna look at the load. So it's getting a lot of load basically, as you can see here. I think I'm just gonna go ahead and look at the database instance and look at the top SQL, the load in the last 30 minutes. Sliced by database, weights, host, database. Anyways, so top SQL commands, top weights. Interesting. There's not a lot of data, huh? Oh, this is MySQL node 1. We need node 2, right? How do we check out for node 2? Can I say node 2? Yeah, cool. Okay. So in the last 30 minutes, we can actually see for node 2, interestingly, oh yeah, that's how you click basically, node 2, node 3. So node 2, now you can actually see that the database load is pretty high. So it has been increasing. If you see lines, so yep, or bars, you see based on user, only one user I think will have it. All the same user, administrator. SQL queries, I think there's a lot of insert into, yeah, and then, yeah, a lot of insert into 20, 22, 17, 19, 21, 23, 24, okay. And then host, only one host I believe, so it's basically this one host. Database, graviton underscore test, so, yep. So waits, yep. So it's waiting on a lot of input output, and then synchronous logs and stuff, right? And then CPU. So you can actually see the top SQL. I forgot the full form of AAS, but anyways, IO CPU, hosts, of course, just one host. Users will be administrator one, the same database. Okay, cool. So you can also look at database telemetry. You look at operating system, database metrics, and also looks. One moment. After doing this, you would look at monitoring over here also. For example, node 2, node 3, node 2 monitoring. You would look at CPU utilization, freeable memory, next review database related, select throughput, DML throughput. So CPU utilization has been pretty high. So can we look at this for last 30 minutes? I think it is last 30 minutes. So yep, it is high. Freeable memory has decreased. You can't free this much this memory, right? It has increased a bit in between, but yeah, it was a lot before, I think, until I started the thing. And IO latency is high. Select throughput, DML throughput. Okay, so you can actually see the queries per second has also increased. InnoDB history list length, connection utilization has also increased, sessions has also increased. And so basically there are 23 metrics, right? So there are throughput metrics also. So DDL throughput, query throughput. So you can see actually DML throughput, DDL throughput. DML throughput is high, and then select throughput is also high. Insert throughput is okay. Delete throughput is low, but DML throughput is high. DML and select throughput are high. Right, so this is 1409 1.4K, and this select is 5.2K, 5.1K, and if you look at it both, yeah, it's quite a bit. So looking at all this, and then after reviewing, look at the whole database insights, top SQL and all. So we have looked at that. InnoDB rows inserted and all that. So this is going to keep going on. So we'll just look at some database insights over here. Not here. Wait a minute. Oh yeah, this is database insights. So here we could have looked at some stuff like, I don't know, CPU utilization has increased. Freeable memory has decreased, and then select throughput and DML throughput. Okay, we wanted select throughput. So throughput has increased in this time. DML throughput has increased, and then finally you can actually look at database insights, which we've already been seeing, in which we'll be looking at InnoDB rows inserted, updated, read, active transactions by looking at logs. So we can also look at logs, of course. So oh wow, if you hover over stuff, I think it will show you things. So I think there is some InnoDB stuff here. Yeah, so if you actually look at logs, I think it might be able to give you the latest logs and slow query patterns. So create table is apparently slow, I think, but other than that, patterns and the queries themselves. So count duration is 1 second. Other than that, this shows the P95 also, I think. So 95%. Just a minute. Looks like you can actually hover over these and you'll notice some stuff like what is weight, this thing. So try multi-row, for example, this something about the number of tables that your sessions are opening exceeds the size of the table definition. Cache or the table open increase the size of these caches. Okay, interesting stuff. Cool. So now if you look at events, OS processes, so you have RDS processes, MySQL daemon and all that, and AWS event loop, MySQL daemon connection, storage daemon, and that's it. Performance analysis, no reports, calling services, and then finally in the database telemetry, you can actually look at specific metrics. For example, you can create InnoDB stuff like InnoDB rows inserted, updated, read. These you can keep inserted, updated, read, and then transactions. So there's no name for this. You can actually give it a name if you want. Basically InnoDB rows inserted. So InnoDB rows inserted, right? Update widget, and then this has increased in the last few minutes, so it's done actually, by the way. So you can actually see, let's do this so you'll actually see it's, yeah, and then updated, and here you can actually do updated, yeah, so, and then finally red, and then you'll also have active transactions. Yeah, so this is one. So, yep, and temp related stuff, there are many things. So with that in place, you'll actually see that these have all increased, right? Let's copy this, by the way. This is, oh, this is some other log, sorry. I shouldn't have put this here. I think I've been using this for some wrong stuff. Okay, just a moment. So I think I've been using setup consumers. Yeah, I think I need to put this over here. Remove this. This is for setup consumers. Red logs. This is fine. Performance schema and all. Setup instruments. Slow query log. Look at these later. Cluster level monitoring script. Okay. So this is my thing. So 11,000, 8,000 and 11,000. Okay. Cool. So this is what I'm looking at, and that's a lot. 3 million, 3.1 million, and then 895k, 447 and whatnot. Now let's look at the next thing that we do. Let me actually let's look at transactions, read, updated, inserted, CPU utilization. Okay. Cool. So now I'll be actually failing over one of these. Let me use this to fail over, right? Let's see if it works. Yeah, are you sure you want to fail over this cluster? Yeah. So the failover happens. Let's see how that works. How that works. Failing over. Okay. Cool. Creating replica. Oh wow, this should be available by now, right? I don't know why this is also taking time. Let me just reload this whole page. Okay, so now it's available. So this is the writer instance now, and this is the reader instance. These are all reader instances now. So let's run the same thing again, right? Once the failover is done, you'll actually see the x86 things, right? And let's run the same thing again, right? Cool. So now let me go ahead and do the same thing again and refresh to see how things are. I want to see, like, I want to see the whole time. Let's see. Oh, that's what it has been showing below. So if I actually choose something, it shows the total below, I think. So let me just choose the total below like this. I think then it will just show this. So this is decreased, like it has come to nothing now. It's almost 0. Now it should increase again in some time. I just can't give a timeline, I think. Oh, the timeline is here, 1 hour. Cool. I can't give any time here weirdly, but I can use it here. maybe I can give 3 hours, and yep, so 3 hours, and now we should be able to see some decrease in free available memory and more increase in CPU utilization. In the last 1 hour, I think it should go down and come back up again actually. So it has gone down, it'll come back up again, yeah. And IO latency will also go up, IO operations, IO throughput, everything will go up, and connection utilization, everything. So this will take some time. Oh, this is on node 2, so this is actually the reader now. So we have to go for this, right? So this is the latest, writer, and you look at the OS metrics, you can actually see the CPU utilization is going high. The rows inserted is not a lot yet, so you can actually see that there are a lot of select statements. You can see what kind of select statements, yeah. These are some examples. These are the patterns. So and then so actually see that a lot of weight in IO and CPU, and top host is just one of them. So this is just the top database is of course Graviton test. Telemetry, you can actually see the active transactions. It should increase. I'm wondering why it hasn't increased yet. I think it'll take some time for it to show up. Probably put 30 minutes and let's see if it refreshes. I'll also click refresh, I think. CPU utilization has increased. For example, if you see in the last 1 hour, it's increasing slowly. Let's see. Maybe last 3 hours, notice that yes, active transactions has finally increased, but that's just 16 or something, very few. That's just very few. Okay, wait. Active transactions is less, but the number of rows is 100k, so it's still good, right? And OS metrics is still not bad, so its CPU utilization is high. Here also you can see CPU utilization has gone up. In the last 3 years, you can actually see that it was all pretty low and then it has gone up. IO latency has gone up, IO operations, IO throughput, connections, network throughput, disk queue depth, sessions has gone up, logins has gone up, history, list length, queries per second, query latency has gone up, query throughput, active transactions versus logs, buffer pool hit ratio, a lot of things, right? So there are more metrics that you can add, but I'm just going to go ahead and you can actually look at last 30 minutes and you can actually see the increase. Oh wow, interesting how the last 30 minutes doesn't show much, or the last 1 hour, but last 3 hours shows something clearly, and last 12 hours also shows something clearly. And if you choose something, it shows that you have chosen between this and this, and yeah, if you choose this, now you can watch this, or you can finally watch the whole thing by doing this. Cool. So logs, I think the slow queries will also show up here. This is still running, so yeah. So slow queries should show up here, and it will show up here. Oh, as of now, nothing. Events, nothing, I guess. Oh, there are some instance shutdown. Okay, so this was long back, and it got reset now during the switchover or the failover. So yeah, operating system or OS processes. The processes include the daemons, storage daemon, and all. RDS processes and are also Aurora connection stuff. And performance analysis, I don't think there are any reports. That's fine. You can look at the monitoring over here also to understand active transactions in the last say in the last 1 hour. So active transactions, CPU, for example, CPU utilization, let's go. 3 hours, period is 5 minutes, or period is 5 minutes. In the last 3 hours, aborted clients, so you can actually see CPU utilization, it has increased up, right? Database CPU load has increased, right? And you can actually see, say, VML throughput, this has increased, right? And then what other thing? Freeable memory has decreased from 15 GB to about around 6 GB. Yeah. So free memory has decreased from 1.29 GB to 952 MB. That is the operating system free memory. And so yeah. What else? Throughput, commit throughput, DDL throughput, delete throughput has all increased. DL throughput. So DB connections, write latency, okay. So you can look at all of this, and in database insights you can actually just look at node 3. So you just click at this and you should go to the database insights, I think. Database insights, and it should take you directly to node 3, I think that's how things work. Interesting stuff. So yeah, and if you click this, it should take you to the RDS console, I think, node 3. Yeah, pretty cool stuff. Anyways, so here I think we've seen everything. This is for the last 3 hours, and we're looking at a rise in these dashboards, rise in data or rise in numbers. The rise is justified because we are running a load test, or we are doing some testing, benchmarking. Finally, we'll have some statistics which we'll be comparing. So yeah. Let's close this. Yeah. Forgot that I'm maintaining this in my local, not here. Anyways, so with this we should be able to compare the results, and then finally you can delete the database, and so you can delete this. By running this lab, you've created additional AWS resources. We recommend you run the commands below to remove these resources once you have completed this lab, to ensure you do not incur any unwanted charges for using these services. Makes sense? Let this run completely, and then I'll delete it, and then I think the failover will happen again. And yeah, cool. So next one is Aurora IO optimized storage. I'll let this run for some time, and then later look at the comparison. Oh yeah, the thing is done. Awesome. Okay, so let's look at this. So here it says 263, 2.6 million, and then 750k, 376k, 3.76 million, 313 transactions per second, and all that. Queries 6271 and all. I think if you compare, this is for x86 stats. Okay, and then we have ARM stats. So let's get this done. Cool. So open editors. Yeah. So here I want the compare selected, and so if you look at this, in x86 it's just 2.6 million. Here is 3.1 million. 895K, 750K here. 376K, 447K. And total is 3.7 million. Here it's 4.7 million, 4.47 million. Transactions is 373 per second, 313 per second, 6,271 per second. Queries, this is 7,460 per second, and it's 4.47 million. Here is 3.76 million. Finally, events per second is also high. Time elapsed is same, 10 minutes, 600 seconds, and then total number of events is 223K, and here is 188K. And latency is basically minimum, average, max. So you can see it's 7 milliseconds. Minimum, average is 42, max is 298. This one is 293, interestingly. 95th percentile is 89. So after 9, so 5% are all based on like above 89 milliseconds. And here 5% is above 70 milliseconds only. So 95% of them are below 70 milliseconds. And the sum is 959. Okay. Threads fairness 1309.89 divided by 142. I don't know, like average and then standard deviation. Okay. Average here is, so here it's 13K or around 14K, and this is around 12K. Execution time is around the same actually for both of them. Interesting. So yeah, I mean, we've compared the results, and now I think we can actually move on to the next one. Let's run this up. Cool. Okay. Okay. So with that, we should be able to go to the next one. I'll probably create one more video on this, and so Aurora IO optimized storage, okay, let me just complete it within this video itself. How much time do we have? We have lots of time, yeah. Cool. So Amazon Aurora IO optimized, it's a new storage configuration that provides improved price, performance, and predictable pricing for customers with input-output intensive applications. This lab contains the following tasks: overview, switch Aurora standard storage to Aurora IO optimized storage, simulate an OLTP workload with sysbench on the Aurora IO optimized and Aurora standard instances. So compare results and observe Amazon CloudWatch dashboard. So the storage configuration is different apparently. So Aurora IO optimized for certain workloads offers improved performance, increased throughput, and reduced latency for the most demanding workloads. With Aurora IO optimized, there are zero charges for read and write IO operations. You only pay for your database instances and storage usage, making it easy to predict your database spend upfront. So Aurora IO optimized offers up to 40% cost savings for IO intensive applications where IO charges exceed 25% of the total Aurora database spend. So Aurora IO optimized is the best choice when your IO spend is 25% or more of your total Aurora database spend. Okay. So Aurora IO optimized is a cluster storage configuration and is compatible with various instance classes. Aurora IO optimized is available for Aurora MySQL version 3.03.1 onwards. So Aurora IO optimized and is available alongside Aurora standard. Customers now have more flexibility to choose based on their price predictability and price performance needs. So this is compute, which is compute is on demand or reserved instance. Storage is standard pay per use. Input output pay per request. Other cost components. Aurora IO optimized, it's on demand or reserved instance plus 30%. I'm not sure why plus 30%. Storage standard. I think you'll have to pay a bit more. IO, no additional charges for read and write. Input outputs, other cost components. There's a star over here. I'm not sure what that means, but okay. And event information is this answer. Okay. Cool. So now next, observe storage configuration. By the way, here we should be able to see this being deleted. Yeah, deleting. Awesome. And this should become the writer here. So 1 has become writer before 2 was the writer, I think. Anyway, so observe storage configuration of Aurora standard and Aurora IO optimized clusters. Note that we've already set up the Aurora IO optimized database cluster with the IO optimized storage type. In this lab, we'll observe the storage configuration of Aurora IO optimized and Aurora standard storage clusters. So you have IO optimized storage and then standard storage. So open the thing and search box, type storage. This will bring up the 2 relevant Aurora DB clusters in this lab, for this lab. So let's look at the databases, storage. So we have these 2, and select the Aurora cluster, Aurora lab IO optimized storage, and navigate to the configuration tab. Under the configuration tab, you'll find the cluster storage configuration section. Observe the current database cluster has been configured with the Aurora IO optimized storage type. Okay, so if you click this basically, go to configuration, capacity, authentication configuration, DB cluster, network type, DevOps guru, encryption, monitoring, authentication, capacity type. Interesting that there is no storage mentioned here, is it? Here it is. No, that is. Okay, got it. It's here. It's basically storage. Everywhere it's mentioned. That's the problem. So yeah, cluster storage configuration, Aurora IO optimized. So yeah, click databases on your left hand pane and select the Aurora cluster, Aurora standard storage, and navigate to the configuration tab. Another configuration tab, you'll find the cluster storage configuration section. So observe that the current database cluster has the Aurora standard storage. Okay, so we can actually go back here and look at standard storage. I think the only cluster we have not worked out or worked with is the upgrade UPG, serverless, and also that's it. Everything else we are looking at. Okay, so here manage IAM roles. No, I don't want to do any of that. Yep, this is Aurora standard, right? So okay. Now that you have verified the storage configuration of the Aurora lab IO optimized and standard storage, we will proceed to the next part of the lab. In that section, we will simulate a workload on these database clusters and observe the results. So cool. So if you're not already open and split terminals, we are going to be running 2 of them, I think. So yeah. And in one, we are going to be using run the following command from the first terminal, and run this from second terminal. So basically, I think the cluster endpoint should be DB cluster standard and optimized. Okay, I think it's already mentioned. The thing is like DB cluster IO optimize. Yeah. So here echo DB cluster standard. I think cluster PG. I don't know what that is. Parameter group. Okay. Cluster standard. Yeah. So basically, in the first one, we are running it on IO optimized, and in the second one, we are running it on this. I'm guessing that the data is already there in it. So the above workload will run for 5 minutes. After letting this run for 2 minutes, observe the CloudWatch metrics instance by clicking on the Aurora standard storage and Aurora IO optimized storage. Next, click on the monitoring tab. So you can see IOPS, right? Aurora IO optimized. So we have run a sample workload in both Aurora IO optimized and Aurora standard. Interestingly, they didn't say IO optimized, they said I optimized. Anyways, so if you go and look here, this is I optimized, not IO optimized. Anyways, next section we'll compare the Amazon CloudWatch dashboards. Okay. So we'll be looking at how these look. So IO optimized and standard. Alright, let's close these. We can close these, I think. Yep. So here in monitoring, you can actually watch there are 108 metrics. I think when you click this, there'll be 103. Okay, cool. I think when you click, you can't click database. You can only click CloudWatch. I think. For database, you need to click exactly which node, writer instance, and now you can actually click database insights. So here you'll notice that the CPU utilization is going up in the last 3 hours, right? You can actually say even 6 hours if you want. Actually, it has been pretty low in the last 1 hour. Interesting. I wonder how it works out in like, okay, let's see, MySQL. So -h db clusters IO optimize. db standard so show databases. It has IO test. Okay, so show tables, connect to Aurora, show tables. So there are tables, okay, over here. So the test data is already there. What about IO optimized? I think this also will work, yeah. And show tables, show databases, oops, not databases, this, yeah, connect Aurora test, show tables, yep, this one also has it. So not bad. So if you look at last 3 hours, maybe you'll notice that, okay, yeah, now it has gone up. So here you can see it's 5% and then it has gone to, I don't know, 32%. And what about latency? Commit latency has also gone up in the last few minutes, from 1 to 12. Alarm recommendations. Interesting. Um, are based on modern best practices. Review the recommended alarms configurations before creating an alarm. There are no upfront costs. You pay only for the alarms you create. For more details, Okay. Cool. So latency, throughput. You can look at commit throughput. This has gone up to 300 and whatnot. DDL nothing. DML data modification is 1.2k, and then insert throughput is some 300. Bytes is 675k. Okay, and here 14 MB network, 13 MB network transfer. Okay, cool. So these are for read, write, and all that stuff. You can look at it. Read IOPS is not much. Write IOPS. Yeah, write latency has increased a bit. You can see write IOPS is 307 here, and milliseconds has increased write latency, and write throughput has increased to 7 megabytes per second. Okay, so this has completely run actually. So this is for the IO optimized thing. IO optimized SQL stats. So you'll have to actually get only these. Everything else is this. Yep. And then finally standard storage SQL stats.txt. This is IO optimized storage. Rename. I can't rename it here. Anyways. So for this one, I'm gonna actually just copy this and put here and then put here and this. Okay, awesome. So now we can just compare these two and see how these are different. Oh wow, that looked very bad. Oh, it's showing up and down, but I'm just gonna do it sideways. Oops, shit. I think I did something. Yeah, I think this is to merge or something. Revert block. Anyways, so you can actually see that when you do this, I don't know, 2 to 4 shit. No. It's not a change basically, so I just want to ensure that I reverse it off. So basically here you can actually see that IO optimized, the read is 4.1 million, and here it's 4.2 million in standard storage. Write is 1.19, other is 598k. Actually it's bad for some reason in standard. Are we sure this was standard? Yeah, for some reason in standard it was bad. Interesting. Cool. So time elapsed is the same, 300 seconds. Transactions it was around 299k. Queries is 598. It's close by the way. 1.1 million, and then here 1.2 million. Here 612k. Here 598k. It's pretty close. And yeah, 19,927 versus 20,404 and whatnot. And the latency is pretty high in IO optimized. That is weird. So the sum is total same, and the 95th percentile is also same, but interestingly the minimum, average, and all. So average is higher, minimum is also higher, max is also higher, the latency. So that is weird. Events average is lesser, events execution time is the same. Anyways, so it doesn't look that great, by the way. So so observe CloudWatch dashboards. This lab will guide you through the process of examining custom CloudWatch dashboards to compare the cost between Aurora IO optimized storage and Aurora standard storage. Navigate. The comparison will be based on the assessment test conducted in the previous lab section. So select the Aurora optimized storage dashboard. Okay, so if you go to CloudWatch and dashboards, let's go to CloudWatch. Let me just, oops, I could have just not closed it. Anyways, let's go to CloudWatch. And by the way, this can be, so this is IO optimized, then standard would be this. Yeah, I just want to look at the metrics, that's all. Say IOPS, right? IOPS is a lot, yeah. And then latency, commit latency, delete latency, DML latency has decreased, by the way, but yeah. And then CPU utilization, it was high some time ago. Yeah, cool. So CloudWatch dashboards, we have a dashboard called Aurora IO optimized storage. You can view various widgets from the custom dashboard to estimate the cost of the Aurora cluster in the standard and IO optimized storage configuration. We'll analyze CloudWatch metrics to determine the storage and IO usage. Essential metrics like total IOPS, volume bytes used will be captured from the widgets, allowing us to estimate cost for a 1 month period. So, oops. So this. So here you can actually see Aurora standard storage. It is 4.44 million. Write ops and all that. Read ops, okay. Million on MB. Here versus monthly workload cost. I think I might have to make it bigger to be able to see it. So in USD, 1.14 hourly compute on, okay. Here it's lower actually for IO optimized, okay. Here it's 4.53, same 9.64, 1.35k and all that. But the cost, if you see, monthly storage cost is higher here. Okay, monthly cost in USD is okay, this much. Hourly compute and IOPS cost. So they're actually getting half the price. Note that CloudWatch dashboards may be delayed for processing the metrics. If required, you can repeat the assessment test to simulate high IOPS environment, as Aurora IO optimized is the best choice when your IO spending is 25% or more of your total Aurora database spending. In this thing, did we actually run only, so this is read and write, not just read, okay. Cool. So in our of a database planning, so in our specific use case, we chose a R6G compute instance and assumed a 2 TB dataset for our Aurora cluster. Based on the sysbench test, this configuration will consistently handle a similar workload during peak hours for the entire month. You can actually observe the Aurora standard storage costs include compute instance and then storage cost and IOPS generated from the workload, estimated over a 1 month period. In contrast, Aurora IO optimized costs solely include compute instance and storage with no charges for read and write operations. So after analyzing the dashboard, you can observe that switching to Aurora optimized from Aurora standards can lower costs for the Aurora cluster if your IO spending is 25% or more of your total Aurora database spending. Okay. So note that preceding costs are high-level estimates and assumptions for the whole month, where storage costs are calculated at the end of the month, not on a daily basis. Sysbench tests have been prepared to simulate a high IOPS environment. Utilize this approach to compute your overall cost estimates, enabling you to make informed decisions when choosing between Aurora Standard and Aurora IO Optimized. For additional details, please refer to this post. Additional pricing, okay. Additional resources use AWS pricing calculator for estimating the cost for your solution. By the way, so this dashboard, what is the? Can I actually add something over here? Yeah, I can add line, data table, number, gauge. This is similar to Grafana. Yep, bar, stacked area. Other content types are also there. Data sources, from where you get the data. You can get it from Prometheus, you can get it from the bucket, RDS, OpenSearch, you can get it from, I don't know, many things. Lambda, I don't know what this is. I think this is Kinesis probably, right? So CloudWatch, Pi Explorer, oh, this is interesting. Hey. Data table doesn't change. It does change. And these change too. Cool. So I want to understand what is the code behind this. View logs in this time range. Okay. What is this? Investigate Aurora standard storage. I think this is AI, is it? Operational troubleshooting, investigate. Okay. Access denied, AI ops list, investigate groups. Okay. So, and then this volume write IOPS, read IOPS. So bytes used. Okay, so this is showing ops operations, write ops, read ops. Okay. The number of write disk IO operations to the cluster volume reported at 5-minute intervals. For a detailed description of how build write operations are calculated, see volume read IOPS. Note that it doesn't make sense to choose a period, choose a -FN period value that's small, because RDS collects this matrix at intervals, not continuously. Count per 5 minutes. View and metrics. Okay. So you can actually. Okay, so the 10 seconds thing is actually. I think it will reload after this. Anyways, so these are the metrics basically. So the label, the details, right? And they've taken the sum basically. So write ops, read ops. So here it says, if you click this again, it will show up the same thing, I think. This and this are the same. Yeah, it's just this has to be bigger, and you're good to go. This, yeah, so it's the same thing. So over 7 days period, some maximum here for total volume bytes used, and then total ops is M1 plus M2, so M1 and M2. Yeah. Y-axis, what is this? I don't know. There's no y-axis here, I think. I mean, it's just labels and stuff. Cool. So the number of build, read, I/O operations from a cluster volume within a 5-minute interval. Build, read operations are calculated at the cluster volume level, aggregated from all instances. Aggregated from all instances in the Aurora DB. I'm not able to get it. Let me close this and open. Okay. From all instances in the Aurora DB cluster and then reported at 5-minute intervals. The value is calculated by taking the value of the read operations metric over a 5-minute period. You can determine the amount of build read operations per second by taking the value of build read operations metric and dividing by 300 seconds. Okay. For example, if the build read operations returns 13,686, then the build read operations per second is 45. You accrue build read operations for queries that request database pages that aren't in the buffer cache and must be loaded from storage. You might see spikes in build read operations as query results are read from storage and then loaded into the buffer cache. Note that it doesn't make sense to choose a -n period value that's small, because Amazon RDS collects this metric at intervals, not continuously. Tip: if your Aurora MySQL cluster uses parallel query, you might see an increase in volume read IOPS. Parallel queries don't use the buffer pool. Thus, although the queries are fast, this optimized processing can result in an increase in read operations and associated charges. So write ops, read ops, bytes used. Okay, the volume of storage used by your Aurora DB cluster. This value affects the cost of the Aurora DB cluster. So for pricing information, see Amazon RDS pricing. This value doesn't reflect some internal storage allocations that don't affect storage billing. So for Aurora MySQL, you can anticipate out-of-space issues more accurately by testing whether Aurora volume bytes left total is approaching 0, instead of comparing volume bytes against the storage limit of 128 TB. For clusters that are clones, the value of this metric depends on the amount of data added or changed on the clone. The metric can also increase or decrease when the original cluster is deleted or as new clones are added or deleted. For details, see deleting a source cluster volume. Note that it doesn't make sense to choose a period -n period value that's small, because the RDS collects this metrics at intervals, not continuously. Okay, so let's click these. I should go back. I should have clicked with control or the command. This read ops, bytes use, pricing. Let's just clone this. Cool. And then we can actually look at, so we can close this. Can we edit this whole thing? Save dashboard as, delete dashboard, view or edit source. Cool. So this is the source of the dashboard. Let me just copy this up. Let me put this as this. IO optimized versus standard storage Aurora CloudWatch dashboard .json. Cool. So we have it, and this we can actually use it to create stuff. So that is that. We can't copy this, can we? Or we can actually. So okay, so now we have done this, we have also read this. Utilize this approach. Okay, we saw the post and AWS pricing calculator for estimating the cost. Okay, got that. And then finally, switch Aurora standard storage to Aurora IO optimized. In this lab, we'll switch the Aurora standard storage configuration to the Aurora IO optimized storage configuration on our provisioned cluster Aurora lab standard storage. Okay, so we'll go here, and this is the standard storage. Oops, and click modify. This is node 1. It's not doing the self-managed IO optimized is basically here. You can probably do this over here and modify optimized. Yeah, now we can click this, I think, and then IO optimized. You can switch to IO optimized only once per month. Okay, cool. So you can switch to this only once per month in the standard storage. One instance will be modified around the chosen cluster configuration. And continue, apply immediately, modify cluster. Cool. So that is going on, and it will be modifying. You'll now be redirected to the database console page. Our Aurora standard cluster will be in modifying status. Your application can still access the database during the state. You have now switched your Aurora storage configuration from Aurora standard to Aurora IO optimized storage configuration. You can switch existing database clusters to Aurora IO optimized once every 30 days. Cool. So next is security. I'll probably do this in another video. Security, global databases, machine learning, serverless, upgrading, and zero ETL. I'll do all of this one by one. That's all I had for this video. I'll see you in the next one. Bye bye.